about 4 years ago, at this exact same time of year, for reasons I can't now recall, an idea for a department seminar series flashed before my eyes. And the idea was that we should get experienced researchers, whether they're on the faculty, the staff, or among the ranks of our senior graduate students, to every once in a while, in a forum like this one, discuss a particular example from their own research careers in which they pursued an idea and had the original theory of the case be proven to be, in retrospect, utterly false, completely wrong. And I thought that doing so, telling such stories, would especially be both encouraging and enlightening to our newest members of the research community. How many of you are first-year graduate students or undergraduates? There's only a few, but it doesn't only apply to such people. It applies to us all, I think. The notion that, but I think the younger among us may not have been able to convince themselves yet, personally, how valuable it is to be wrong sometimes. And so I want to, in the spirit of that idea, tell my story today. It's maybe my highest profile example from my own career of pursuit of trying to understand the forcing for vertical motion in the occluded quadrant of cyclones, and how I was utterly wrong with what I presumed would be the answer, and how thrilled I am now in retrospect to have been so wrong, because it led to insights I did not bargain for at the beginning of that process. And so that's what I hope to do today, and I hope that some of the more senior researchers in the group will take up the mantle and do this exact same kind of thing in the future, because I think it really is a valuable story to hear experienced people who younger people assume are never wrong, perhaps, admit publicly that they've been wrong and that their wrongness has led them in a new direction. So that's where the title for my talk comes from today. Wayward hypotheses need not occlude progress. You can learn a lot from having made a mistake, even if it isn't really truly a mistake. So the first winter I was here, I was lucky enough, Pete remembers this, the first winter I was here, I was lucky enough to have a really cold, snowy winter. And if you don't know me very well, that's my favorite kind of winter. It's in fact my favorite season. And so this was a storm that occurred on the 19th of January, 1995. Just 2 or 3, I think it was the Friday of the last week of the winter break. So the next Monday we were going to start classes. Maybe it was even Tuesday, but it was the next week we were going to start classes. So this was my first break between semesters of my entire career here, and I really needed it. And had to get some things in order research-wise and whatnot. And on this last Friday of that break, we had this fantastic snowstorm. We had about 14 inches of snow in my own backyard, so it's very memorable. All day long, I went from the window to computer screens and various other things, watching the storm and looking at it in the observations, as well as in Greg Tripoli's non-hydrostatic model simulations, which were being animated for me on Viz 5D. So I was like a kid in a candy shop, and in the truest sense of the word. So here's the amazing snow totals that occurred on that day in a band that stretched all the way from Green Bay, or actually the Door County Peninsula, down to about Tulsa. And in Columbia, Missouri, they had more snow in this one day than they usually have in an entire cold season. So this was a really remarkable snow event. But it occurred in the context of a relatively weak sea level pressure minimum. I've drawn this is my own hand analysis. I drew them every 2 millibars, you'll notice, to make it look more dramatic, because this was a very undramatic surface disturbance. The sea level pressure at this time, 0Z on the 20th, was only 1,000 millibars. 6 or 7 hours or before, it had been 998, and it had the gall to drop below 1,000, but it was barely below 1,000. So this is a really weak sea level pressure minimum. And by what you can see on the analysis here of the surface cold and warm frontal positions, it doesn't really look like much of anything. So, a dime a dozen kind of storm. But when you get away from the surface and start to look at the thermal structure away from the surface is when the real surprises start to show up. And this is another subjective analysis, hand analysis, of equivalent potential temperature at 700 millibars at 0Z on the same day, 20th of January. So you see here, these are drawn every 2 degrees Kelvin, and so you see this really intense baroclinic zone, moisture and baroclinic zone, characterizing the cold front and the warm front, and this wrapped up spring-like structure that goes all the way from eastern Michigan through the southern part of our own state down to the southeast toward Cape Girardeau, Missouri. That's the characteristic warm occluded thermal structure. A beautiful cyclonically curved thermal ridge, very dramatic in this particular example. And as luck would have it, I had sounding data available on nearly a perfect line from St. Paul, Minnesota, or Minneapolis all the way down to Atlanta. And perfect in the sense that I'm able to cut the axis of the maximum theta E ridge almost perpendicularly with the cross-section, as well as get darn close to perpendicular to the straddling baroclinic zones. That's a really nice situation to be in if you're trying to understand the structure of this whole thing. So look at this vertical cross-section. Goes all the way from St. Cloud, near St. Paul, all the way to Atlanta. So there's a bundle of isotropes that I've shaded here in blue that represent the cold frontal portion of this structure. I think that becomes evident once you see the shading. And then this red bundle represents the warm frontal portion of that structure. And so we have this beautiful, almost canonical, warm occluded thermal structure taken, as I tell my class in 452 all the time, effectively at random. Because this is a real case, and I didn't get a chance to prescribe these conditions, they just showed up. And right in between the two baroclinic zones, there's an upward sloping axis of maximum theta E that actually slopes poleward and westward in this case. And in the region of, in between the two fronts in the middle troposphere, the stratification is relatively weaker than it is anywhere else. So all sorts of interesting things about the structure of this storm are occurring as I'm looking out the window. Oh, sorry. And these elements of the warm occluded structure I didn't discover. This was known by Bergeron in the late 19-teens and early 20s in the Norwegian school, and then Saussure had a really nice book on kinematics and structures of mid-latitude cyclones in the mid-50s. And this is from Saussure's book. I've appended the isotherms in the dashed orange on top, but there's a picture in a plan view of an occluded cyclone, where the warm front, cold front meet at the triple point, the peak of the warm sector, and then there's an extension to the west from the peak of the warm sector to the middle, up to the central minimum and low pressure, and that's the occluded front of the surface. But Saussure was wise to show the vertical extension of the cold front right here, and that'll show up later on in some of the analyses that I'm going to do. I've superimposed sort of a column average isotherms or thickness lines on top of this structure to give you an indication that one of the leading structural characteristics of this type of a cyclone is an occluded thermal ridge that really goes from the triple point to the position of the sea level pressure minimum. And in the vertical cross-section from A to B that's indicated on the top panel is shown here, and you can see this is the cold front ascending and actually having already ascended, first encroached and then ascended along the warm front, lifting what had been surface warm sector air into the middle troposphere in the occluded structure. And you can't lift air that's moist and warm without consequence for precipitation. So there's going to be some type of association between the development of such a structure and the development of precipitation as well. And one can only go so far with the conventional observations in terms of getting a really nice picture of the detailed temporal and spatial structure of some of these interesting, even synoptic scale features like an occluded structure in a storm. So I was able to, on the day that I was watching it out the window, I'm looking at Greg Tripoli's model output. And here's one example. Greg has his model, the NMS model is in step coordinates, eta coordinates, so one looks at heights, not pressure levels. This is at 2 kilometers, it's theta E at 2 kilometers, at about 800 millimiles or so. And you can see it slightly earlier than the time I just showed you, but you can see the same elements. Here's the cold frontal structure, here's the warm frontal structure, and then there's this axis of maximum theta E that 6 hours earlier is displaced a little bit further to the south in the evolution of this storm, but it cuts right across the Mississippi River at about St. Louis. So I can also look at cross-sections through the model data. And so I'm going to look at one here that mimics, as you can see, some portion of it mimics the St. Paul down to Atlanta part of the cross-section, but I have extra stuff on the edges. So the cross-section looks like this. This is equivalent potential temperature every 3 degrees Kelvin. And I'm going to particularly concentrate on this portion of it, which more or less mimics the St. Paul to Atlanta portion of the cross-section. And you can see it has the exact same elements as the observations had at 6 hours later, this bundle of moist isotopes that characterizes the cold frontal portion of the structure, this bundle of moist isotopes that characterizes the warm frontal portion of the structure, and an axis of maximum theta E that goes upward and westward from that, between the two baroclinic zones. And notice how poorly stratified the air is. D theta E dz is very small and positive in this location compared to anywhere near the cold front or anywhere near the warm front. So all of the characteristic elements of the occluded thermal structure are captured in the model. But I thought to myself, this isn't, you don't want to just take a series of vertical cross-sections with this gorgeous high resolution in time and space data. You want to do something more creative with it. And so I thought, maybe this would be interesting. Let's try and examine what the topography of one of those moist isotropic surfaces is, throughout the whole evolution of the storm. And I could build it from looking at it at just this one time. So my initial idea was, here's the warm edge of the cold frontal baroclinic zone, 312 Kelvin. It also is the warm edge of the warm frontal portion of the structure. So I thought, maybe I'll take a look at what the topography of 312 Kelvin is. Turns out if you're right on the warm edge, you lose a little bit of the spatial and structural continuity as you move forward through the evolution. So the next best thing is to take the next higher value of theta E, 309 Kelvin, and that's what I did. And then I exploited this on a million other storms. I could do it right now, upstairs, in 2 seconds for any storm you pick across either hemisphere, and you'll be able to see this. It's foolproof. And I know what I'm talking about as an experienced fool. So, 309 degrees Kelvin, and watch what you see. Okay, so now just before I show you, first of all, it will change your life forever if you've not seen it. You should be ready for that. Secondly, think about what I'm going to show you. I'm going to show you a plan view of the topography of this surface. So how I've constructed that. I've decided to look at the whole continental US, because that's about the area that I have for this particular simulation. First I plot, where is the 309 Kelvin theta E isotrope at 0 meters above sea level? Where is it then at 1 kilometer above sea level? Where is it at 2 kilometers, and so on? And I lay them on top of each other. And that's what you get. Wow, huh? It looks like a giant treble clef. And doesn't it? Comes down in like this. The shading represents how high you are above the surface. And you can see some elements here that maybe need a little explanation. First, the jagged but relatively steep cliff in the theta E surface that you see in the southeast United States represents the cold frontal portion of this structure. So right here where Hurricane Michael just made landfall, you have 1, 2, 3, 4, 5, 6 kilometers in that short distance across the rest of the panhandle. So that's a really steep upward slope. That's the cold frontal portion of this thing. Less steeply sloped, but still discernibly sloped, is the warm frontal portion across the upper Midwest. And then what this thing reveals that I hadn't seen before and changed the way I thought about all this was that the surface actually rolls over itself, and there's an upward sloping canyon where that rollover takes place. And that extends from somewhere in Indiana, I can't be sure about where, and neither could anyone who lives there, to be honest with you, and then rotating back up cyclonically towards about Kansas City. So that's really intriguing. This structure is right there. Now, once you do it at one time, of course, you get this beautiful high-resolution in-time data set. You can look at how this structure evolves. And so here it was at 0.6Z. You can see both the shallowly sloped warm front and a steeply sloped cold front, and just a little bit of this wrapped over surface upward sloping canyon that's probably hidden by that little crest right in there across northern Arkansas. As the storm gets more intense and the circulation gets more intense throughout the column, then you get both the warm and the cold front, and you get a little bit of a lengthening of that interesting curled over structure. Here's the 18Z plot that you just saw, and then by the time you get to 0Z on the 20th, that upward sloping canyon extends all the way from western North Carolina through southern Wisconsin back down south of Kansas City. It's unmistakably there, and the structure is still maintaining a cold frontal and a warm frontal portion of the structure. So there's a whole new way to look at the whole three-dimensional structure of an occluded cyclone. And I thought, this is really exciting, but it's not new, because the Canadians in the mid-1940s came up with this schematic idea of a trough of warm air aloft. It's an anagram that stands for that. But I drew this picture of what the trowel conceptual model really is trying to show, based on what I'd seen in my analysis of the 19th of January storm. And so let me explain what's on here. First, you've got the surface warm and cold fronts and the surface occluded boundary, which is often analyzed in the pressure trough at sea level. And then you've got aloft the warm edge of the cold frontal baroclinic zone in light blue and the warm edge of the warm frontal baroclinic zone in pink. And then what's interesting, and the Canadians were onto this, the Norwegians probably were too, but didn't really push it, is that the intersection between the warm and the cold fronts is actually a three-dimensionally sloping line. It's not just one line, because it slopes upward and poleward to the west. And so here in the yellow and black dashed line is the position of that trough of warm air aloft, the apex of the intersection of the cold and the warm fronts, and it slopes upward in 3 dimensions. And if you project its position in space down to the ground, it almost always is coincident with the region of heavy precipitation in the western or occluded quadrant of the cyclone. And notice there's a disjuncture between the precipitation band in the occluded quadrant and the position of the surface warm occlusion. Because the whole production mechanism doesn't care about this thing. It cares about this. And so we have to pay attention to what's driving the ascent in the trowel portion of the occluded quadrant of the cyclone. That became the new question for me. What's driving the ascent there? And I thought, that's a really worthy question. And so decided I wanted to pursue that. And I can show you this in animation. Somehow the animation got a little bit screwed up here. I hope you can still see through it. This is from Viz 5D. I'm showing you the animation of the 309 degree Kelvin theta E surface from this storm, 19th of January. So there's the little wrapped over portion of the structure, the upward sloping canyon. You see where it's going. Okay. Aside from this stuff, you can see the shading there too. If I then superimpose the position of the snowband, and that's just the axis of it, you recognize instantly, upon watching it once even, that there's a strong relationship spatially between where the snow fell and where this interesting trowel structure progressed across the central part of the country. So there's something of value here in trying to understand the relationship between why that structure drives vertical motions and the result of the vertical motion in a winter storm is a heavy snowband. So pretty interesting. And so far you haven't seen anything about, another perspective on this, but I can tilt, the Viz 5D viewing plane in any orientation that I want. This is a view elevated and from the north, so here's Canada, Minnesota, Wisconsin, and this is the edge of this yellow line is the particular air parcel trajectory, and I'm letting you see where it came from, but where it is always at the end. And you can see it going right up the gut of this three-dimensional sloping intersection between the cold and the warm fronts, this trowel structure. So it's almost like a wave crests, and right at you're surfing that wave right in that trowel. And while you're surfing, you're dropping 15 inches of snow on Columbia, Missouri. Actually 22, way more than their average for a year. So pretty impressive structure. And you get a sense in this particular depiction that there's vertical motion involved, but you get a really good idea of that by looking at a plan view of this, or a side view, cross-section view of that trajectory from the east. Every X represents a 6-hour time signature, so this is from 0 to 6 to 12 and so on, and then there's the elevation. So the parcel doesn't rise much in the first 12, but then from 12 to 18 to 24 hours in the simulation, it rises nearly 7 kilometers. So this is synoptic scale vertical motion on the order of 50 centimeters per second for half a day. It's not surprising that it was a snowball. But that's a huge amount of synoptic scale vertical motion. Okay, it's a order of 10 times larger than normal. So it's really substantial event. And as I said, I'm gaining more and more interest in trying to diagnose what drives the vertical motion in this thing. So that's where this is all building. But this is all just showing you how it was motivated. There was a lot in there that was worthy of investigation. So if we think of just a typical mid-latitude cyclone, and these fronts, the cold and warm frontal symbols that are on this map, were actually affixed based on analysis of, say, in this case, low-level 950 millibar theta E, as well as 950 millibar vorticity. So wherever the gradient of the theta E is strongest, and it's coincident with a strong vortex structure, you put a front there. And so those things were not placed at random, and they have a nice relationship to elements of the cloud mass in this storm. But schematically, those frontal zones are going to delineate regions of strong baroclinicity, and these are schematic isotherms or isotropes in yellow. And if I remove everything from this picture, because it starts to get a little bit confusing or a little cluttered, if I remove everything except the isotropes and the circulation, a sense of the circulation around the disturbance in the lower part of the troposphere, given by these green schematic arrows, you get a sense that's not surprising. These baroclinic zones are being compressed by the circulation, the deformation in the circulation particularly, so that the absolute distance between successive isotherms gets smaller if the only thing that's acting on them is the kinematic wind field around the cyclone. And that process is known as frontogenesis. And if these baroclinic zones are frontogenetically active, they will force thermally direct circulation. So air will rise on the warm sides of the cold front and the warm side of the warm front under the influence of differential temperature advection that is frontogenetic. So this is kind of leading me towards, I've got an idea for how this works in the occluded quadrant. Here it is. The blue lines are schematic isotherms, or call them average isotherms, thickness lines, whatever you want to call them, any measure of temperature. You can see the fronts are fixed on there and the low pressure center is back at the terminus of the occluded thermal ridge, which is occupied by the occluded surface front in purple. And I thought to myself, hey, the occluded thermal ridge is flanked by baroclinic zones, cold front and the warm frontal baroclinic zone. If those are both frontogenetically active, then the warm side of both of those baroclinic zones is in fact the occluded thermal ridge. So my hypothesis was, hey, this would be an easy problem to solve. No one's thought of it. I can't believe it. It's low-hanging fruit. Frontogenesis along the flanking baroclinic zones of the occluded thermal ridge is going to be the mechanism that forces the upward vertical motion in the occluded quadrant of the cyclone. Great, that'll be easy to write up. I gotta move on to the next thing, 10 years, 3 years down the road, or whatever it was. So, I had a lot of options for how I might go about calculating this frontogenesis. One can either use the full wind with the temperature field, one can maybe do something that's a little bit more flexible and look at this process from the quasi-geostrophic perspective. Because then you can invoke some other types of analyses on top of just looking at the frontogenesis. That's what I opted to do. Lucky that I did. So I thought I will look at this process of frontogenesis from the QG omega equation perspective, and that requires use of the Q vector. So I decided I was going to take a Q vector perspective on this problem. And for those who have never seen or heard of the Q vector, it's really nifty. It's worth your time to think about it a little bit, but I'll tell you some of the highlights. This is the left-hand side of the traditional omega equation. It's effectively a three-dimensional Laplacian of omega. And that is forced, mathematically, by minus twice the divergence of this completely hypothetical vector that Hoskins, Dragici, and Davies came up with in 1978, 40 years ago now. What a great year for the omega equation. Q is given by this. These bold V's are vectors. So it's the ddx of the vector geostrophic wind dotted with del theta. That's a scalar itself, but it's given the I direction. This is a different scalar, dvg dy, dotted with del theta. That's given the J direction. That's what the Q vector is. And long arguments have been made that say this is really the best way to look at the forcing for a quasi-geostrophic vertical motion. There's plenty of people who will argue with me. Louis Uccellini did it publicly. It's now on the web about this. And of course I won. So, and if I told him that, he wouldn't like it. The thing about Q that's interesting, instead of using the omega equation or any other sort of variant of it, is the following thing. That physically, Q represents the rate of change of the vector del theta following the geostrophic flow. No other form of the omega equation gets you to burrow down and be able to say something physical and mathematical quite like this. So in other words, Q is the rate of change following the geostrophic flow, so that's going to be partial derivative plus UG ddx plus VG ddy of the whole vector, del theta. And any vector has two components to it. One is its magnitude, one is its direction. So that means that Q can describe changes simultaneously, describe changes in the magnitude of del theta as well as the direction of del theta. So any arbitrary Q vector, like this one in purple, here are isotropes, can be split into orthogonal components. One of which we'll call Qn is in the direction of the vector del theta. So naturally it will determine whether this vector gets longer or shorter. It changes the magnitudes of the potential temperature gradient. Qs, the other component, is going to only change the direction of del theta. So that's rather interesting. So, armed with this, and still with this hypothesis in mind, I thought, this is interesting. I'm going to look at all of the across isentrope Q vectors, Qn, the ones that govern the length of the vector del theta. Those are going to tell me my story in the occluded quadrant. Of course they will, because if I have Qn pointing from cold to warm, this is cold to warm, if Qn is just an incremental change in del theta, in this case its magnitude, I will have made the gradient stronger. That will be active frontogenesis. And so I'll have warm air rising because there's convergence of the Q vector on the warm side in such a scenario, and cold air sinking, just what I expected. So this was, in fact, the kernel of my working hypothesis. When I apply this diagnostic, it might have been on a Friday that I had the idea, and I came in the next Monday, hands like this, saying, here it comes, I'm going to see my answer. It was going to be, the occluded thermal ridge was going to have Qn vectors, a cross-isotrope component of Q, cutting across the isotropes and converging in the thermal ridge. And that was going to give me all my vertical motion. I was certain I was going to see that. But to be complete, I wanted to make sure I had in mind the other component of Q, which is the along isentrope component of Q. And all it can do is change the direction of this vector, because it's orthogonal to it, but it's going to have regions of convergence and divergence, like any vector field might. And where it converges, you'll have ascent. Where it diverges, you'll have descent. This won't produce vertical motions that straddle the thermal wind, or are parallel, in other words, to the thermal field. It will be along the thermal field, so I had to make up a name for it. I got yelled at about this by people who won't be named. I call it shear-wise, because it's along the shear. That makes sense to me. And no one's really complained since. Person who complained wished he had thought of it himself. That's my contention. It's often the case.
Who that was, you're not going to tell.
I'm not going to say it. It's nobody who works here. But I can tell you, young researchers, if you think scientific research is immune to all the political mischief that humans inject into everything, you are dead wrong. It'll still happen. So you just have to game yourself up for that. Get ready for that. It can be fun, though. So here's where I went. To the 1st of April, 1997. So here I am, a couple of years in here, and one storm after another is pummeling various parts of the country with all of this interesting weather. They're nicely occluded systems. So I'm kind of compiling a list of these storms in case I ever get past the point where I am not ignorant anymore of what's going on, which up to this point I certainly still was. This is the 1st of April, 1997, a major blizzard in southern New England. They had 30 inches of snow in Boston, I think, that day, 30 at my house in Peabody, which is on the North Shore. And all on April Fool's Day, so fantastic. Again, these frontal zones are placed here by analysis, not just to make the picture look pretty, but it does look pretty, doesn't it? And so there's a cold front, a narrow warm sector, and then there's an extended occluded front by the time you get to 06Z on the 1st of April. So that's the time that I'm going to look at. I'm going to go right to my Q-vector diagnostics and say, what is the column average from 500 to 900 millibars Q-vector field, and the vectors you can't really tell, but they're there in black. And then the convergence only of the Q-vector field, because the convergence is related directly to forcing for vertical motion, upward vertical motion, sorry. And so here's the picture, and the shading represents the intensity. So where it's blue and green, you have really intense Q-vector convergence along this line, and then over here there's little pieces of kind of weaker convergence along into the south of the main convergence region. So I was expecting the lion's share of this total Q-vector convergence was going to be accomplished by Q sub n, cutting across the isotropes, the across-isotrope Q-vector. I was not correct. Here is the partition. This is not labeled incorrectly. This is the QS convergence, the along-isotrope Q-vector convergence, and this is the across-isotrope Q-vector convergence, the part that governs frontogenesis. So, and I had to double the shading interval here just to make it show up, because it's so weak. So when you take the total, these two sum precisely to that, the lion's share of the total forcing in and around the occluded front, and therefore in the occluded quadrant of the cyclone, is produced by this along-isotrope Q-vector convergence. I was dumbfounded. This is where I was 180 degrees off on the right track. And so here's the point where if you decide to, you can say, well, you know, I've got another problem to work on. I'll come back to this because I don't really get what's going on here. And I don't want to pursue it right now. I want to work on something else that I feel like I have more knowledge about. Or you can say, if you're me, I almost never have another problem to work on, so I have to just kind of, you know, carry the ball as far downfield as I can. So I'm thinking I'm going to have to stay with this now, but it's going to be a little more challenging. But boy, was it interesting. Wait till you see. So this was a big surprise. And I should say, I looked at, as I had compiled my list of storms, this wasn't the only one I was looking at. I looked at January 19th. I looked at a couple of other ones that I'd made that whole couple of years, and they all showed me the same thing. So there was something systematic going on here that was completely counter, not just counter, opposite to my impression. Very interesting. So where do you go next? I started to draw schematics. I had to try and understand what I was even seeing. So these are all conceptual schematics. So let's imagine I have a zonally oriented bunch of isotropes in red, and then I have a region of, and I'm not going to tell you how I get it, I don't know yet. But let's just imagine I have a QS convergence maximum in the middle of that bundle, and that's the football-shaped green region, and the axis is the dashed black line. And on either side of that axis of maximum convergence, of course, I have a vector del theta that's pointed, in that case, in the same direction, from cold to warm. But remembering that QS, being a part of Q, is going to change the orientation of this vector del theta as much as it'll change that one. But since QS is pointing in opposite directions, in order to afford the convergence, it's going to differentially rotate those vectors del theta. So they'll start out as they are, just redrawn them here. But on the left-hand side, it'll be turned counterclockwise. On the right-hand side, it'll be turned clockwise. And remembering also that QS cannot change the magnitude of the potential temperature gradient, only the orientation. I can't make those isotropes in my redrawn picture, which I'll show you in a minute. I can't make those isotropes have any closer absolute distance to each other than they did in the first picture. Okay? So here's what I get. Here's my new del theta prime on that side. Here's del theta prime on that side. I've tried to keep the absolute spacing the same between the isotropes. Look what I get. I get forcing for upward vertical motion and the production of a thermal ridge. Are you kidding me? Wow. So thank God I was wrong. All of a sudden it dawns on me that there's an underlying dynamical process going on here that I still don't know the details of yet. But there's an underlying dynamical process that does two things for me at once. It tells me why there's vertical motion in the trowel and why it snowed 14 inches in my backyard. And why is the occluded structure so characteristically associated with a thermal ridge? And why is that thermal ridge always vested with strong ascent in it and production of heavy snow? All at once. Came out of nowhere. And so this was a blessing. I put in the abstract. It's a blessing when you're wrong, if you keep on following it sometimes. And this was certainly such a case. So I wanted to break this down a little bit more. So far, we've been thinking about it only in terms of these vectors. But is there any lurking mathematical relationships that are underlying the concept that might provide more insight? And so that's where I went next. So I wanted to break down this QS vector. And the place where I get it in the first place is I just use a simple vector calculus identity. If you want to take the component of Q along this vector, it's the dot product divided by the magnitude of the second vector. So that's a scalar. Everything in red in here is a scalar. So is that. And then everything in blue is a vector. So I just assign my scalar quantity, the vector direction, k cross del theta, and the magnitude of del theta is the same as the magnitude of k cross del theta, so I just make it look a little bit simpler. Okay? But then you can unpack this thing mathematically, and you get some interesting results. So here is what it looks like. It's going to be magnitude of theta over 2 times f times a constant gamma, which was introduced by Eliasson. It's a way to write the hydrostatic equation in terms of potential temperature instead of temperature. And then you have two properties of the wind: geostrophic vorticity, total geostrophic deformation, and some weird trigonometric function. And then the vector part stays the same. So again, unpacking all of this, or just actually doing the algebra. Del theta divided by del theta goes away. F sigma over 2 times that for the vector field, times eta geo, and so on. You end up with this. Twice the divergence of this quantity is F times dV GdP dot del geostrophic vorticity, and then this. That's because minus gamma times k cross del theta is the thermal wind. And that comes right from the hydrostatic equation in this rewritten version. So you've got thermal wind advection of geostrophic vorticity. Well, anybody who's studied synoptic dynamics in this department knows they've heard that before. And then there's thermal wind advection of this weird trigonometric function of geostrophic deformation, terms A and B. Well, A is the contribution, as I said, from PVA by the thermal wind. Exactly what Sutcliffe found in 1947, and Trenberth followed up 40 years ago this month, actually. And then the second term, B, is non-frontogenetic geostrophic deformation, because it's sine of 2 beta, not cosine of 2 beta. All this will do is rotate the baroclinic zone. And it turns out you can also think of this in a more conceptual way. A and B are the forcings for quasi-geostrophic vertical motion that result from the rotation of the vector del theta that's made by the geostrophic vorticity and by the geostrophic deformation, respectively. So there's a role to play for geostrophic vorticity and deformation in simply rotating a bundle of isotropes. And by doing so, vertical motions appear out of nowhere. Well, out of the omega equation. But isn't that interesting? Wouldn't have thought that. So there's another way to break this down, and that is to start with the original expression I had before. And you might remember this from the prior time. And then decide that you're going to say, since one of these terms, as I just mentioned, represents how the vorticity rotates the baroclinic zones, and one represents how the deformation does, let's just split these into their own vector quantities. And so we'll call the vorticity contribution Q sub VR, where VR means vorticity does the rotating, and that's 1/2 of the Trenberth force. And then Q sub dr, if you unpack this whole thing into its Cartesian expression, means, dr means deformation does the rotation. Then you find out that there's specific reference to the geostrophic shearing and the geostrophic stretching deformation, F1 and F2. And it's got an ugly Cartesian expression. But, you know, ugly. Who cares about ugly now? You can just calculate them all on the computer, so it doesn't matter if they're ugly. You can still do them, right? So, but just to prove my point, if you put a bundle of isotropes in a pure vortex, there's no doubt that you're going to rotate that bundle, and by doing so, you will change the orientation of del theta. So vorticity can rotate del theta and not change the magnitude. And then for certain angles at which you insert that same bundle into a pure deformation field, you will also do only rotation. After a certain point, the rotation is combined with some compaction or some eradication. But at certain angles, all you'll do is the rotation. So certainly these two things are quite possible. So I decided I wanted to do, the next thing was, I wanted to look at how does this Q sub S forcing, which produces, as you saw, by far the largest portion of the total vertical motion forcing in the occluded quadrant, how does that split up into these two contributions, which summed together give you the whole thing? So I wanted to see, I want to keep cutting this thing into as many individual pieces, physically relevant individual pieces, as I could. And again, keep in mind how far away I am now from my original hypothesis. I'm on this trail, you know, the branch is that thick. And I'm hoping that I don't get to the end and it just breaks off. But I'm really encouraged that's not going to happen. Because every time I take a turn along this path that I've been sort of directed by my own ignorance at first to fall upon, it keeps getting more and more interesting. So here's what I did. I went back to the the April 1997 storm and looked at an evolution. And the evolution is going to involve splitting the total QS convergence in the 500 to 900 millibar column into its separate pieces that sum together for the total. So here is at 15Z on the 31st of March. 950 theta E is in green, sea level isobars are black, and then the frontal positions are, again, placed there by analysis. Where's the gradient of theta E strongest? Where is that gradient strength coincident with the largest cyclonic vorticity? So that's how I put the fronts there. They're really fronts. And you can see they line up nicely with the thermal field. And then here's the column average Q vector, QS vectors themselves, and their convergence. And so you get this big blob right sort of at the northern end of the Chesapeake Bay, which is just to the north or just to the west of the cyclone center, and is beginning to develop. And then when I split that up, here is the QVR component. This is just the PVA by the thermal wind piece of that forcing, and this is the deformation piece of that forcing. And so at this early time in the cyclone life cycle, much of the total signal is residing in the Q sub VR, the PVA by the thermal wind. Almost none of it is in the deformation piece. Okay. So that was interesting. I didn't know what it meant yet. So I go to another time. 9 hours later, the cyclone's moved to the northeast. It's a little bit more intense. It's down now to 988 millibars or something. There's now an occluded thermal ridge, even at 950 millibars in theta E. So there's a nice occluded thermal ridge there south of Cape Cod and the islands, and there in cold and warm fronts and so on. Here's the total QS forcing in the same 500 to 900 millibar column average, and we get a big maximum just south of Long Island Sound. And now I want to split it up again as I did before. A little bit different this time. This is the PVA by the thermal wind piece. It has a maximum right over Long Island, which is again just to the north and west of the minimum in sea level pressure. Something interesting about that, and I'll point that out later. Then, by virtue of the fact that I have this little bit of a thermal ridge finally, I didn't have it at the prior time, right along its axis, I have a really strong Q sub DR convergence maximum. The deformation has been mobilized, and it's acting vigorously to produce forcing for vertical motion in that location. Now, something else that's interesting about this upon inspection is that if one looks at what is it about the Q sub VR vector field that produces convergence over Long Island, it turns out it's that the vectors themselves just get smaller. They don't change direction. You can get convergence from a vector field if that happens, and that's what's going on with the Q sub VR vector field. Not true for Q sub DR, and this is going to matter later on. Right along the axis of the maximum forcing, look at the vectors, if you can see them, they're diametrically opposed on flanking sides of that axis. So they are acting to producing their convergence by coming from different directions. It's not true for the other piece. So we'll keep on going. This is now 12Z on the 1st of April. By this time, the storm has not moved very much from its minimum, from its prior location, but what has happened is the length of the occluded thermal ridge is considerably longer. So that's extended. And here's the total Q sub S forcing in the column, and you might not be surprised to find that Q sub VR, the PVA by the thermal wind piece, just offshore of Cape Cod, is again to the north and west of the sea level pressure minimum. It's consistently in the same spot relative to wherever the central minimum is at sea level. And I think that's because the PVA by the thermal wind piece of this forcing is sustaining the vertical motion that maintains or even deepens the cyclone a little bit. You've got to take mass out of that column to keep it low or to make it lower. Meanwhile, the lion's share of the total forcing is right along the thermal ridge, and once again, convergence of the QVR vectors is a function of the vectors themselves getting smaller as you head toward the center of the convergence maxima, not changing direction. Not true for Q sub dr. The deformation vectors are exactly opposite one another across that axis of maximum forcing. So very different geometries, and the only reason I point that out, we'll see later on, but I want to just give you a little highlight. We can't forget that both of these vector fields on the bottom, QVR and QDR, are telling us how the geostrophic flow is rotating baroclinic zones. That's all it's telling us. And so if you have differential directions, you have differential rotation. And that's really interesting, as it turns out. Okay? So here's what I think the role of the geostrophic deformation is. The red lines represent an initial thermal field that has just begun to produce a little bit of a thermal ridge. Okay, so there's a second derivative of theta across this boundary. That's, or there's a second derivative of theta in the whole domain. There wouldn't be if it was uniform straight line isotherms. And so as soon as there's a little bit of a thermal ridge, a little bit of a second derivative of theta in the domain, the deformation is mobilized. It's impotent until then, it turns out. And there's a mathematical reason that you can trace back. But as soon as there's a little bit of a thermal ridge, it's mobilized. QDR is the most substantial portion of that deformation field, and it's going to be oriented parallel to the isotherms, as I've drawn it here in purple. Here's the original orientation of the flanking, of the del theta vectors on the flanking baroclinic zones astride the thermal ridge. And if you add QDR to that, you get a new del theta prime. If you add this QDR to this one, you get a new del theta prime. And look what's happened to the isotropes. It's like there's a hinge adjoining that thermal ridge, and it gets closed. The thermal ridge gets lengthened, and there's simultaneously forcing for vertical motion right at its axis. So it's not even the vorticity that's doing this lengthening and closing of the hinge of the thermal ridge in the occluded quadrant, it's the deformation that's doing it. But it's not frontogenetical deformation, which is what I thought it might be. Totally opposite. Oh, so excited. So eventually all of this stuff congealed in my head, and I had this new dynamical conceptual model of the occlusion process. And I could have covered up some of these diagrams, as is my tendency, but I didn't do it. So these are both equivalent. But the first one shows a bunch of column average isotropes in red, so the thermal wind will be parallel to them. It's colder on this side, warmer on this one. You can't see the labels. And if you have a upper level vorticity maxima, well then down shear in the thermal wind sense of that vorticity maxima, you have cyclonic vorticity advection by the thermal wind, which, according to Sutcliffe, Trenberth, and the omega equation, will produce upward vertical motion, which I've colored in green. Now you can equally represent that exact same forcing in terms of these Q sub VR vectors. And when you do that, you not only get the same answer for the vertical motion forcing, and consequently the vertical motion, but you get new information about how the baroclinic zone is being restructured in the presence of the geostrophic wind field that allows all of this to take place. That is, since this is cold and warm, del theta is cutting across this way, this series of QVR vectors is going to reorient del theta to the north and reorient it to the south. So you're going to produce a little bit of a thermal ridge right where you have your forcing for vertical motion. That's a function of this rotation accomplished by the vorticity. You can think of it this way. Michael Morgan said this to me one time, he's right on. Think about there just being a vortex here in the vorticity maxima. Then on the north side of it, you're going to push the isotherms that way. On the south side, you'll push them this way, and that's what you get. But you also have information about forcing for vertical motion. Once you've got a little bit of a thermal ridge, as I mentioned before, the deformation is mobilized. Q sub dr vectors come into play, and they start to change the orientation of that bundle of isotropes so that they become stronger and stronger in terms of the closing along the thermal ridge. It's like a hinge being closed. And that's a function of these Q sub dr vectors, whose convergence, remember I mentioned this and made a point of it, the vectors in the deformation piece in the April storm had opposite direction astride the thermal ridge. If they don't, then I can't close that thermal ridge and make it longer. So that's all part of the process of producing the thermal structure, but then vesting at the same time that thermal structure with forcing for ascent. And that's how it shows up on weather maps and in your backyard, if you happen to be me on the 19th of January, 1995. So I was way off target when I started this research project. And it ended up taking 2 or 3 years to get to the end of this thing, but I was way off target. And in fact, I think looking back now, my original hypothesis, had it been true, would have been the most nondescript scientific paper of all time, because it would have been exactly according to everyone else's expectations too. And you know, you would have done it because you kind of want to make sure you're moving ahead and you've got something you can show the National Science Foundation you've contributed to the literature. But there's a difference between contributing to the literature and contributing to the science. And it's a lot more fun to contribute to the science. So when you end up, as I did, quite by accident, being on the wrong path, but then having it being made so clear to you that you were on the wrong path, that it was worth it to keep on the right path as it was being unveiled to you, you just can't beat that. That's what makes scientific research so much fun. So if any of you are at the beginnings of your careers, and I think it applies, I give myself this pep talk now, 25 years in, so I think it applies to all of us. If you're at the beginning of a new project, don't be discouraged by throwing a hypothesis out there that ends up not being right. Figure out why it isn't right. Perhaps in its wrongness, it's going to point you in a direction that you didn't expect, and you'll be able to make a contribution to the science as opposed to a contribution to the literature. So thanks very much for your attention, and I hope others will take this up and do the same thing in the future. Thanks a lot. Stefan.
As expected, this was a great hour.
Oh, thanks.
Not expected is that you talked us only what went on in your own brain.
Yeah.
And indeed, there's a lot going on of the same kind outside your brain, among the other things.
Yeah, yeah.
And there are also these sort of things that can obstruct it. Just a few examples. You take the thing in the 60s, 70s, West African countries became independent, and the drought started. It's probably those Africans, they don't know about how they keep their land and agriculture. There were suggestions made on what they should plant. That it was really one of those long-term droughts and sort of changes coming that one didn't know it. Take another thing, intertropical conversion zone. There was, people believe to know, it's a thing where coincide the low pressure maximum, and that's also the confluence and the convergence of maximum, and that's where also then sort of disturbances travel with the rainfall, and then it's a completely different. No, it takes a long time to realize that. And you can go on with these sort of things. There are lots of these sort of wrong perceived sort of notions and conditional stability of the second kind, and you go on, and it takes a long time to get in it, and it takes when the people the courage of getting to something that may not be in that what is sort of they expect. Or another little thing I know we had was Peter Lamb in the sort of late stage of the paper, and we had ITCZ, and there was intertropical divergence zone. We had it in one graph, and well, we got it from the editor back, and I didn't know it, but Peter, that he noted it. Look, they changed one letter from intertropical divergence zone. They made that D into C. We had to correct that.
Yeah.
Well, that's a bit for the editor. There is no divergence zone. It's just an convergence zone. So it's again, these other brains have it.
Yeah.
But you have to clean up those other. It's not that easy to clean up the other people's brains.
Yeah, I was lucky to be...
have courage, young folks.
Yeah, that's right. I agree with that. I was lucky to be immune from any outside influences of coincidence or other, nefarious types of interpretations when I was pursuing this. So people were very encouraging of this along the way. I think I made sure I talked to people who I suspected would be. And then when I was in my own community at cyclone workshops and presenting aspects of this, they were always quite supportive of it. So I was lucky about that. There's times where you don't get that. One of my good friends in Seattle, Art Rango, was dead set long before anybody else had believed that cloud seeding was not really financially viable and wasn't really even scientifically viable in the way that people were attempting it in the 60s and 70s. He once went to Montreal. He said he gave a 2-minute talk where the talk before his, which was equally 2 minutes, was a rebuttal to what he was going to say. So there are such things as hostile environments arranged on purpose to make your life miserable. I've not had that, so I'm lucky. So be prepared. Brett.
I have a question. So you said the deformation, it has a way of rotating the baroclinic zone, but then it can also eventually, the baroclinic zone can take advantage of the confluence.
Right, that's right.
Is it always preferentially being rotated so that it can take advantage of the confluence, or does it depend on orientation? Does it get into an opposite sense where difluence can blow it out?
That I don't know. It's a good question. Once I got onto the QS piece and then split it into its two components, I didn't think about interactions between the two. So that's still, as far as I can tell, that's still an open question. There may well be a systematic location or systematic set of processes within the cyclone life cycle that set baroclinic zones up for failure and along the lines that you're suggesting. It's quite possible. It'd be a really interesting thing to do. I do know that, at least for a large part of the life cycle that I've uncovered here and shown you today, there's never a time where QN suddenly does come in and say, oh, well, now that you've set the table nicely for my baroclinic zones, I'll stop to do some quasi-geostrophic frontogenesis. The full wind does do some frontogenesis in the occluded quadrant, but you can't partition the pieces the way with the full wind that you can with the Q vector, so it's hard to know exactly what the vorticity and deformation, non-frontogenetic deformation contributions are in the full wind. So you're kind of left in a difficult spot there. But there may well be some interaction after a certain stage, and I've not looked at that. Oh, Karen, sorry.
Yeah. So my brain's about to explode, so can you just spell out for me how this helps in weather forecasting?
I'm not so sure it does. You know, we have numerical forecast models that'll tell you where it's going to snow.
Okay.
And it's funny, I always get that question. I always get the question, how will this tell us about forecasting, as if that's supposed to be the way that, you know, one pursues the work. No, it's more an understanding of what's going on.
Okay.
And it leads you to an insight and a comfortable set of insights about the weather. For me, I can tell you the honest feeling, when this all came out, I just remember walking home in a light snow event, which I knew was in the occluded quadrant, and I was thinking to myself, you know, for thousands of years, people have been snowed on by snow in this part of the storm, and I know how it's working. And that was a great feeling. And whether the forecast was right or wrong, I didn't care.
1st of April?
Huh?
It was on the 1st of April?
No, I was watching that storm in clear skies, desperately homesick about it. But that's actually spurred some other things that I've worked on.
We've had snow here on April Fool's Day.
We had snow here on 17 days past April last year. So, yeah, I know, we can still get it. Brett.
Well, I'll point out one thing where it might intersect with forecasting. And this sort of leads from some of the stuff we discussed with Alex after defense. The regions of high deformation are strange beasts, and they tend to throw some presupposed balance assumptions out the window when you're in a region of very high deformation. So I would imagine that a model that is based on those balance assumptions, especially a model that's initialized with an analysis that was based on those assumptions, may struggle tremendously exactly in the region where this deformation is taking place. It could be that it's partially responsible for some snowfall bust style forecasts.
Yeah, I hadn't thought of that. One thing as you're talking about it, that makes me, it's a companion comment, but not as physical as yours. But if one uses the stripped down approximations to the QG omega equation, such as developed by Sutcliffe or Trenberg, you'll never get any of this out of there because it's all in the deformation term. and they kind of both assumed, well, we can neglect that. Well, you can neglect that unless you don't want to forecast the snow accurately in an included structure. So yeah, you're right. It's very true. So there is some value even from the operational side. But my primary focus is always on just trying to understand how these things work. Any other questions, Maria?
Do you have a hard time publishing this? You know, I think...
No, and in fact, it's funny you ask that question, especially in the context of Stefan's comment, which is right on. It happens sometimes. I've had more trouble publishing things that were more rote, incremental extensions of insight than something like this. I think the reason is because there was no field that had already been plowed on this stuff. It really just came out brand new because of this accident. And so there was, maybe it caught people saying, "Blah, blah, 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 what do I say to this?" And you get it through, and then maybe they complain about it now. But I had one little complaint, actually. When I split QS into QBR and QDR, somebody said, "Well, you're doing too much of this partitioning, it can't all mean anything." And I said, well, okay, and this was one of the reviewers, I said, okay, if that's true, tell me why I'm wrong about what I'm saying it means. No response, radio silence. And so the editor was wise enough to say, in response to the no response, there's no reason to not publish this. And so, you know.
There's no reason to not publish.
Right, that's right. So a lot of double negatives there, but you get the point. Sometimes that happens, but I was lucky to not run into that. It wasn't challenging an established view. People stopped thinking about occluded cyclones in the 1940s, except for me and Dave Schultz. And, you know, so, and his colleague in Manchester. So nobody's thinking about them. They should have been, but nobody is. Melissa?
But, I mean, in my head, storms that occlude are storms that are like kind of overturning and exhibiting like an LC2 life cycle.
Yeah.
And people think about wave breaking all the time. They just aren't usually synopticians.
That's right.
So I think,
That's right.
you know, and that's kind of what I've been thinking about the whole time, is that you're massively rearranging your surface theta gradient in a way that maybe makes it more barotropic. If you look at the upper troposphere, or if you start, you know, kind of a certain pattern that gets locked in, what you see with serial wave breaking.
Yeah.
So maybe it's just not really called that, but that's part of the link that's missing between.
Well, that could very well be. And then a question arises, maybe you could do this with an idealized model. Watch an occluded cyclone in an idealized model get so wrapped up that the barotonicity weakens around its edges. What is it that drives the barotonicity downgrades it? I don't know which one of these processes would be doing that. That'd be an interesting thing to look at. And then to see, do you get a characteristic distribution of vertical motions that comes with that process? So that'd be really neat, and it might provide an easier, you know, plug-in for thinking about it from the wave breaking perspective than just watching an individual storm get to its most mature stage. Maybe. Any other questions? Okay, well, thanks very much for your attention, and I hope somebody else does it.